I'm Riccardo Inverni, and I work in the annual energy statistics team, where I'm in charge of electricity statistics. And today I'm going to present you an overview about electricity and heat. I'll talk a little about recent trends in electricity, followed by some key concepts in relation to electricity statistics. And of course, we'll have some more time at the end for questions on your side. To start with, some key electricity trends. Here you can see a very interesting graph of the evolution of world electricity production between 1974, when the IEA was founded, and 2023. Over this period, world electricity production increased year after year, with the exception of 2009, following the economic crisis, and 2020, due to the COVID-19 pandemic. Overall, this resulted in a five-fold increase in electricity production from roughly 6,300 terawatt hours in 1974 to more than 30,000 terawatt hours in 2023. And I have a little quiz for you. Can you guess what was the main fuel used for electricity generation in 2023? Just some seconds to think about it. Okay, I see. So you are super quick. I see a lot of answers in the chat, and all of them are correct. It's coal. Very good. And here we have now a graph which help us to better understand that. So over this almost 50 years period, the mix of fuels used to generate electricity, of course, changed according to the time. For instance, if we look at the share of electricity production from oil, we can see that it passed from about 25%, it was in 1974, to less than 3%. So it was a dramatic decrease of electricity production from oil. Similarly, also the share of hydro has fallen from it was 23% to around 15%. And this is because many suitable large-scale sites have already been exploited. And of course, by contrast, we need some other fuels to increase in order to balance this decrease of oil and hydro. And we have the share of production from natural gas, which increases significantly, rising up to 22% of generation. There is also a noticeable increase in production from nuclear, which passed from 4% to roughly 9% in 2023. And of course, there is also the very important rise in the share of solar and wind, which now represent the 13% of electricity production, and which were absent back in 1974. During this time, you will notice that coal still remains the main fuel used for power generation, as you correctly pointed out. And its share is changing very little during the years, and it's always around 35–36%. Of course, the main reason for coal's enduring popularity is its relative cost advantage over the other fuels. But we can observe more in deep and more closer the data for electricity generation in 2023. So as mentioned, coal remains the dominant fuel, providing 35% of electricity generation. This is followed by natural gas, which provides around a quarter, I would say, of the total output. And in total, 63% of electricity is produced from combustible fuels. So coal, oil, gas, biofuels, and waste. Now let's have another look at the electricity production, but divided by region. So this graph shows electricity production from OECD and non-OECD countries, and you can see how trends differ between these two groups. Within the non-OECD countries, trends also differ like very, very importantly by region. If we disaggregate non-OECD production, we can see that much of the growth in recent years has been driven by China and other countries in non-OECD Asia. But if we have a look at the same graph, but highlighting different concept, um, electricity production in non-OECD countries has grown much faster than in OECD countries over the past 20 years. So as a result, production in non-OECD countries surpassed the one of OECD countries back in 2011. And since then, electricity production in non-OECD countries has continued to increase, while production, or we can say that production in OECD countries has reached a plateau. And in 2023, non-OECD countries produced the 63% of the global electricity production. Here, we have a look at the world electricity consumption by sector. So, first of all, we can notice how also the consumption increased 5 times between 1974 and 2023, growing from 5,000 to 25,000 terawatt hour. And if you remember, like really a few slides back, we saw that the production also increased 5 times. So let's say it makes sense that consumption would increase by the same amount. But you can point out that the numbers are different. So if you remember, production in 2023 was around 30,000 terawatt hour, while here the final consumption is only about 25,000 terawatt hour. So what is the reason for the gap between production and final consumption figures? We will have a look more in detail in some following slides, but I can anticipate that this is due to transmission and distribution losses, and also the own use inside the energy industry. What is the own use in the energy industry is the electricity used for power plants, for lighting and supporting the activities, and also in the energy industry activities such as mines, refineries, oil and gas extraction sites, etc. Looking at the consumption by sector, globally, we can spot how industry is the largest consuming sector. However, its share of consumption has declined over time. This is due to the restructuring and improvements in energy efficiency, in particular in OECD countries, where the electricity demand in industry now is rising at a lower rate than in other sectors. However, again, this is a graph for the world, and we can disaggregate this behavior by regions. And you can see how dividing, for example, OECD and non-OECD countries, the behaviors are really different. So in non-OECD countries, which is the graph on the left, we have 3 sectors: industry, residential, and commercial and public services, each consuming around 30%, 32% of the total electricity demand. By contrast, in the non-OECD countries as a whole, of course, industry represents almost half of the total electricity demand. Again, now we are dividing just between OECD and non-OECD countries, but this behavior may differ a lot at an individual country level. So these were some global, let's say, electricity trends. Now let's have a look more in detail to some key concepts relating to electricity and heat, and especially to electricity and heat reporting. So electricity can be produced as both primary and secondary energy. Primary electricity is obtained from natural sources such as hydro, solar, PV, wind, and tidal and wave energy. Secondary electricity is obtained from the heat generated by burning combustible fuels, from nuclear fissions, from geothermal heat, and from solar thermal heat. Similarly, heat can be produced as primary and secondary energy. Primary heat is obtained from natural sources such as solar thermal and geothermal, as well as nuclear fission. Secondary heat is obtained by burning combustible fuels from transforming electricity into heat in electric boilers, or using heat pumps to capture heat from low temperature sources. Let's have a look now at the producers. As you may know, electricity and heat producers can be divided into two categories: the main activity producers and the auto producers. So main activity producers generate electricity and heat for third parties as their primary activity. It means that the main purpose of the facility is to generate electricity or heat. For instance, if we think about a nuclear power plant, we have the little logo there. This is a perfect example of a main activity producer. By contrast, an auto producer generates electricity or heat only as a secondary activity in support of their primary activity. So again, another example, for instance, a large chemical facility may have an on-site power plant to generate electricity or heat for use in the production processes, and some of this electricity or heat may also be sold. However, the main purpose of the facility is to produce chemicals, not to produce electricity or heat. So that's why these would be classed as an auto producer. And it's very important because it's something that we discussed many times with our contacts, with the countries. It's important to note that this distinction is not based on whether the plants are public or private, but on their primary activity. So main activity producers and auto producers can be public or private companies. So the ownership is irrelevant. We have also three different types of plants. Electricity-only plants, which, as the name suggests, only produce electricity. We have heat-only plants, which again generates only heat. And also we have the combined heat and power plants, or CHP plants, which can generate both electricity and heat in a combined process. This distinction is important. These two distinctions that we made, so main, auto, and the three kind of plants, it's important because we have some reporting convention used in the reporting of electricity and heat statistics. And this is very important and fundamental to report correctly electricity and heat statistics. For the main activity producers, the convention is very simple. So all production of electricity and heat is reported from all plants. For the auto producer, the situation is different. So for electricity, all electricity produced is reported in the questionnaire or in the statistics. However, only the amount of heat sold are reported. The amount of heat generated for own use on site, those are not reported. Similarly, when reporting the associated fuel inputs to electricity and heat production, for heat, only the amounts of fuel input associated with heat sold are reported. So this is very important. I added a note because, like in the for the annual questionnaires, for those reporting with the annual questionnaires, in the new questionnaires, there is also the option to collect now the heat auto-consumed by auto producers. This is just a note that I wanted to add. Another important concept, which sometimes can be confusing as well, is the distinction between gross and net production. Gross production refers to the total output of electricity or heat generated in a facility before any amount of energy is used. Not all of these, of course, not all of this energy is used beyond the power plant. Some of the energy, some of the electricity and heat generated, they are used on site at the power plant for lighting, heating, supporting the plant operation. And this is called own use. So what we call net production is the difference between the gross production and the net production. And we also have a reporting conversion from own use, and this is due to the reporting conversion that we discussed before about heat in auto producers. So again, for main activity producer, the convention is very simple. The net production is equal to gross production minus the own use. For auto producers, we only report the amount of heat sold. Therefore, it doesn't make sense to speak about own use. We assume that gross production is equal to net production and that there is no own use. This is because for auto production of heat, it's very difficult to distinguish between the heat used for own use and that used support the heat supported. Sorry, the heat used to support the plant operations. Now we have covered, I would say, the tricky part of the presentation because the reporting conventions are always very tricky and very difficult sometimes to understand. Let's have a look now to the electricity and heat supply chain and to some of the data that we collect in our questionnaires. So in terms of supply, what we collect are the fuel inputs to electricity and heat generation. Of course, the gross production. There is also the own use, the net production, which, as we explained, is the difference between gross and own use. We also collect information of the electricity used for pumped storage, hydro, for the boilers, and for the heat pumps. And finally, on the supply side, what we collect are also the trade, so the exchange, the import and exports of any country with respect to the others. On the consumption side, sorry, before the consumption side, of course, very important, we have the losses, which we mentioned a little bit before. So during this transmission and distribution, we have some losses that I will explain later more in detail. But for the final consumption, sorry, we also collect data on final consumption depending on the different sectors. Finally, we also collect data such as peak load and capacity data, which can be useful for electricity analysts. So as I mentioned quickly before, transmission and distribution losses occur between supply and consumption, and they are responsible, like they are one of the reasons why there is a difference between the values of supply and the values of consumption. So just to give you some more detail on the magnitude of the losses that can be expected and why they occur. As electricity travels through cables and transformer, energy is lost during the way. Much of this is in the form of heat because when electricity is flowing through the cable, it raises the temperature. This energy is lost and dissipates into the surroundings, reducing the amount of electricity that reaches the final destination. Let's say that in general, losses can be expected to be in the range from 5 to 15%, I would say. And of course, losses are lower in more advanced and well-maintained grids and higher in older or more distributed grids, or also where there is a high rate of meter bypassing, so electricity theft. This is what we were discussing before. If we consider the global gross electricity production, we have the value of around 30,000 terawatt hour, but just 84% is able to cover the final consumption, so the demand, because around 16% is lost in the unused and losses. As we highlighted during the presentation, the difference between the gross production and the final consumption is mainly due to unused and transmission and distribution losses. Of course, there is always a statistical difference, which is the difference between the two, that can also occur. Now I would like to speak about some concepts that can be really useful as checks when reporting electricity and heat data. And the first of all is the generation efficiency. Efficiency is calculated as the total gross energy produced by a plant divided by the energy content of the fuel used to produce it. So basically, it's the energy output over the energy input. There are some rules. Of course, since energy cannot be created from nowhere, efficiency needs to be lower than 100%. The efficiency differs by fuel and technology. If you think about a coal power plant or a combined cycle power plant using natural gas, generally the combined cycle has a way higher efficiency. And it must be calculated in energy units. So what I want to say is that we need to use energy units, and we need to use the same energy units for the inputs and for the outputs. So this is a very simplified example of a power plant using 100 units of energy as input and producing 20 units of electricity and 45 units of heat as output. And the general efficiency of the plant, then it would be 20 plus 45 over 100, so 65%. It's interesting also to discuss about trade, because we have a unique reporting convention for trade in electricity. This is because unlike other fuels, trade of electricity and heat is reported on the basis of the borders crossed, not on origin and destination. This means that we include the amounts in transit. For example, if we have an export of Portugal, an export of electricity to France, it needs to pass by Spain. Portugal would report these exports to Spain. Spain would report both the imports from Portugal and the export to France, and France would report the imports from Spain. Another concept which I find useful to discuss always is the difference between energy and power. Let's say that simply put, power is the rate at which energy is used or produced, is the energy divided by time. But what I want to stress is the difference between watts, which are units of power, and watt hour, which are a unit of energy. And finally, a discussion about capacity. What we defined as net maximum capacity is the maximum power output that can be supplied on the 31st of December, so the last day of the year, of the reporting year. These are very useful data for analysts to have, but they can also be very useful for us, for statisticians, when checking the data to understand if the data reported are consistent or not. For example, we can compare the actual reported production with the maximum potential production to check if this data makes sense. This is called capacity factor. What is the maximum potential production? The maximum potential production is the production that a power plant or a country would have if producing a maximum capacity all the hours, all the seconds of the year. So it's capacity multiplied by time. It's a very useful check. Again, it should be lower than 100%. And of course, has different expected values depending on technology. For example, a solar PV, very simplifying, cannot produce at night or when there is no sun. So we would have a capacity factor way lower than a nuclear power plant, which I expect to run as much as possible, and which I expect to have a capacity factor very high, around 90%, if not higher. Just would like to quickly mention a couple of facts and information about the data collection and the types of data collection that we have. Let's say that with all statistics, data collection has a cost in terms of time, money, but also in terms of opportunity cost. Therefore, a balance must be struck between available resources and needs. This said, I like very much to stress the fact that not having the proper information available for informed decision making can lead to higher cost in the future. In the terms of specific challenges for electricity statistics, the liberalization of electricity markets has had an impact, of course, because previously, where there were monopolies, all the electricity data could be gathered from one company, but now data needs to be gathered from many different companies, and this can impact data coverage and comprehensiveness. And in terms of data collection system, to facilitate the data collection, we should, of course, establish a legal basis, establish a proper reporting mechanism, allocate proper resources, as always, and establish also a proper dissemination scheme. I will conclude with the types of data collection that you can have. We can use surveys, which are extremely comprehensive, but very often they present a high burden. They are very time consuming and they are normally expensive to manage. Second source of data are administrative data, which very often are not collected primarily for statistical purposes. They are usually collected for implemented programs or policies or for companies to run their business. But that can be really useful. For example, think about energy regulators having information on the type and capacity of the licenses for power plant that they issue, or TSO, transmission system operators, which have information on the amount of electricity passing through their networks and also across the borders. Of course, we can also gather data via direct measurements, for example, in the cases of smart meters, and this would be perfect if it would be available for all the things that we need to measure. And finally, also estimation and modeling allow to have data quantified when actual measurements cannot be obtained. If you want to learn more about the IEA energy statistics, we have a lot of different resources that can be helpful. And you will find here in the presentation some useful links to many IEA products that we publish on our website.